Good morning, everyone. I'm excited to talk to you about our paper that we've titled Boxed Out, Blocking Cellular Interconnect Bypass Fraud at the Network Edge. And I promise by the end of this talk, you'll actually know what that means. So I'm Brad Reaves, and this was joint work that I did with Ethan Shernan, Adam Bates, Hank Carter, and Patrick Traynor. And we were at either the Florida Institute for Cybersecurity at the University of Florida or Georgia Tech. Now, I don't know if you saw it Wednesday, but there was actually a really cool talk on black markets in Tor hidden services. If you missed the talk, go check out the paper. It was cool. So I thought I would start my talk with a black market that I found not on Tor, but on LinkedIn. So these are messages from managers at small telecommunications companies. Some of them may resell service, or some of them may actually sell the calling cards that you see in your local store. And what they're doing is they are seeking out the cheapest routes that they can to route their local calls into other countries, in places like Senegal and Ecuador and Ukraine. Now, some of them are looking for legitimate providers, folks who terminate calls illicitly and according to regulations. But some of these messages, though, are secretly looking for special carriers that actually sell at a low price because they're illegally connecting to other providers to deliver calls in ways that the providers that they're connecting to actually aren't even aware of. So you're probably asking yourself at this point, how does somebody connect to a telecommunications company without them knowing? This is an interesting question, and here's one way you do it. This is Alice, and she wants to make a call to Bob. Alice is in the United States, and let's say Bob is in Ecuador. So Alice has gone to her store, she's bought one of these little calling cards, and she's going to pay 5 cents a minute for this call. Now, the way she uses the calling card is she picks up her phone, dials a 1-800 number, and what her local carrier does is terminate it, which means to deliver the call, to the calling card provider. And so to her network, this just looks like a normal local call, and her network has done its job. But her call doesn't stop there. Instead, the calling card provider forwards her call over the internet and into Ecuador. Now, there's nothing wrong with this step, nothing wrong at all with doing telephony over VoIP. We think it's a great thing. But the problem comes in at this next step. It's not delivered to a licensed telecommunications provider in Ecuador. Instead, it's delivered to a group who have a bunch of what are known as VoIP-GSM gateways. Now, the gateways that these groups will buy typically will hold 10 or 20 SIM cards at a time, and so they've become known as simboxes. It's kind of a cool word, so we're going to continue to use it. Now, from the simbox, the call then is passed on to a local call over the cellular network that the simbox places. And it's finally forwarded to Bob as if it were a local cell phone call. Now, to the carrier in Ecuador, this looks like a perfectly legitimate local call. And in fact, the network can't distinguish between this call that's come all the way from the United States, has traversed several other intermediate networks, and the one that is placed by a legitimate provider on a local phone. Now, an analogy might help for those of us who don't always work in telephony. This is akin to if you were an internet provider and you started selling service, but you peered with another ISP by freeloading off of their Wi-Fi in the office. That's kind of the working analogy here. And the whole point of the setup is to deliver the call into carrier B in Ecuador without paying for the real interconnection with that carrier. The right way to do this is to go to that carrier and say, I want to connect with you. I want to do so in a building where we can regulate and monitor and properly build these calls and ensure that call quality is achieved. So carriers have a word for this activity, and it's called interconnect bypass fraud. So that's half the title. We're already there. But we're going to use the term simbox fraud for this talk. And there's a few reasons for this, one of which is that it's actually a lot easier to say. That was a joke, you can laugh. All right, so before we go further, I want to convince you that this is actually a very real problem for carriers. So the cellular networks that we all know and love are necessarily provisioned under assumptions, including how many calls are made in a given time for a particular cell, which is to say the particular tower that might be serving all of us here in this room. Now, and these assumptions are necessary because there's only so many towers available, and there's only so much spectrum available. And so there are physical limits to what a cellular network is capable of supporting. In particular, it does a great job, thanks to the engineers who build these things, of supporting the load of users like us who maybe place a few calls a day of an average of 2 minutes in length. They're not good, however, at supporting the load of an unlicensed telecommunications provider who's making dozens of calls simultaneously all day and all night. And so there's a few results of this on the network. First of all, the network gets overloaded. But the call quality is terrible because you've hopped through a bunch of steps to deliver the call that wouldn't occur in a regulated call. If you happen to be walking near one of these simboxing operations, you're going to have to share the tower with that simboxing operation, who's likely tying up most or all of the lines currently available at the tower, which means you're not going to be able to place a call. And it costs carriers $2 billion a year. It's especially important in developing nations where they use a lot of the telecommunications revenue they receive, especially from international calls, to fund development in their own countries. In Ghana, they lose the equivalent of a World Bank loan every year to this. So now that I've hopefully convinced you that this is a problem worth solving, I want to present our solution to this problem. We call it Ammit, and the name Ammit comes from an Egyptian funerary deity who devoured the souls of those who are unworthy to enter into the afterlife. We thought it was a great metaphor for a system that shuts down illegal calls. So the key insight behind Ammit is that I told you that call quality is bad, and so the insight is that Simbox audio will sound different than legitimate call audio in distinct and measurable ways. And because of that, we're able to detect individual calls in real time, which no other system can do currently, and we do it at the tower servicing the Simbox. We do it there for a few reasons. One, it lets us get the best audio possible to analyze, but it also means that if we detect a call and we're confident that it's being Simboxed, we can end it immediately, rather than waiting months for the billing cycle to roll over. Ammit can go further than that, though, and it can also work on individual SIM cards that are being used in these Simboxes. So the idea is maybe after 20 calls, you can identify that this entire SIM card in this account is being used strictly for illegitimate purposes, and it can be disabled. And this is the real trick to defeating Simbox fraud, because Simbox fraud is fundamentally an economic activity. It's a business, and if you can cause the costs of business to be unacceptable, then effectively you will hopefully do away with the problem. So I want to show you, give you some insight into some of the things that happen in audio that make Ammit possible. In particular, I want to talk about 3 sources of where audio degrades in a Simbox call. So this is our call from Alice to Bob. In the first place, working left to right, that you see audio changes are in the source network. Now, most telephone systems nowadays are no longer analog, so you don't get any of the cool static and hiss and things like that. But what you do see are digital transmission errors. So the cellular phone system uses digital audio, which means it's packetized. And so if Alice drives in a tunnel or is stuck down here in a bunker with no cell reception, her call quality is going to be bad. And that's something that can be measured. The second thing that can happen is that the audio degrades as it's transmitted over the internet in the VoIP step. And we'll talk a little bit more about the ways that VoIP can damage audio, but it also has to do with the packetization. The last place that the audio can degrade is actually over the air as it's transmitted from the Simbox to the tower. And I want to deal with this question first. But I do want to note that you'll notice that both legitimate calls and Simbox calls have to deal with over-the-air degradation. But the other 2 sources would never, ever affect a legitimate local call. So we need to deal with this issue of air losses that degrade the audio in ways that affect both legitimate and illegitimate calls. And the first thing you should know is that cellular networks actually see typical loss rates of somewhere around 4 or 5% per call. And so the network has tricks to cover this up that we'll talk about in a few minutes, but it's actually a very lossy connection because of the wireless medium. So the solution to this, to detecting this and making sure that we filter out these audio problems instead of others, is to keep track of the call audio frames that are lost, and the tower can tell when this happens because the checksums fail. So basically, you just have to keep track of every packet that the tower knows is bad. Which leads us to dealing with the main source of audio degradation that we focus on in this work, and that's the degradations that happen in VoIP. We tend not to focus on the source network degradations for a couple reasons. One is it would require a lot of assumptions about where calls were coming from, and it would vastly complicate our evaluation. So we took a conservative approach and assumed that the audio coming into the simboxing operation was perfect, even though that's probably never going to be the case. So what that means is our results are simply just conservative. Now, so you may be asking yourself, VoIP is digital. We've got this internet thing, so the call quality should be perfect. Again, you're not going to see the hisses that you used to hear on old landline phones. So VoIP degrades basically only when packets are lost or when they're so late that they might as well have been lost, meaning that a packet gets delayed, and by the time the packet was supposed to be played by the phone, it hasn't arrived. So when these losses occur, a VoIP client, which in our case we mean the Simbox, it can do one of two things. Either it just plays silence through the gap and waits until it gets a good packet at the proper time, or it can try to actually conceal these packet losses by generating audio that should sound okay to a human ear. These things are never perfect, but in general, they do a pretty good job of covering them up. And it's why when you have a Skype call, it sometimes just starts to sound weird when it goes bad. So these techniques are called packet loss concealment algorithms, and they've been the subject of research in the VoIP community for about 20 years. So there's a few different flavors. So now that we've talked about where these problems can come from, let's talk about how we detect them. And let's start with the unconcealed losses. So this is just when there's silence on the line. And we can use a technique that we borrowed from the pin drop project and use a technique from speech processing called computing the short-term energy of audio. Basically what this does is it gives you sort of a reference of basically how loud the audio is at a given time. And if there's a very brief section where the energy drops and then rises again, roughly corresponding to the length of a packet or two, then we know that we've had a lost packet, especially if that drop and rise happens in too short a time to have been natural speech. Now, there's a caveat to this technique, and that is that it can only work when someone is talking. So on average, unless you're a politician, you're talking about 50% of the time. And so what that means is that this vastly reduces the number of losses that we can actually detect. But this allows us to keep track of the unconcealed losses that happen in the VoIP step in a Simbox call, but never happen in a real call. So let's take a look at this problem of packet concealment. And in particular, we focused on the algorithm that's used in the GSM codec specified by the GSM cellular standards. So GSM actually has its own audio codec and its own way of dealing with lost packets. It's why when you drive in a tunnel, it doesn't go silent. It just sort of goes, ah. That was funny. You can laugh at that too. We looked at this packet loss concealment algorithm for a few reasons. One is it's widely supported by Simboxes, actually. There are public implementations of the codec, and so lots of VoIP clients use it. We also thought it was actually going to be the hardest case to defend against because they're using the same codec as is actually used by the legitimate calls. The third reason was that it allowed us to innovate in the space of packet loss concealment. Other work had looked at other algorithms, but we wanted to look at this one because no one had. The fourth reason it's a good thing to look at is that it actually occurs in the source network. So while we weren't focused on the source network, we knew that if we could do this, we would catch a lot of errors that happen at the beginning of a Simbox call for free. So the way that this codec works is fairly simple. As soon as you lose a packet, the phone you're using, or the VoIP client or whatever, replays the last good packet and makes it just a little bit softer over time. And so what this means is it almost creates an echo on the line. And so we can use a technique from signal processing known as cepstral analysis to detect these echoes. So let me show you what this looks like in a graph. Above we have actual speech, where the first 20 milliseconds are good signal, and then the next 40 milliseconds are actually lost packets that have been filled in by this GSM packet loss concealment algorithm. And if you kind of squint it, you can see that it's basically the same thing repeated, but just at lower amplitude. And at the bottom, what we've done is shown you a cepstral analysis of these 3 frames. And in particular, there is a huge spike at exactly 20 milliseconds. And what this means is that there was a repeating audio happening in exactly 20 milliseconds, like an echo. And so this is probably a lost packets in GSM. And we know this because a peak at 20 milliseconds is actually very, very rare in human speech. So it turns out that this was actually a great way to distinguish lost packets from good packets. So after we developed these techniques to detect Simbox audio, we needed to test them to make sure that they were correct. And so we started with a simulated Simbox call. And we went with simulations for a few reasons. One is that I've mentioned some factors already that we needed to control for. So the loss rate is going to have an effect. The codecs used on the VoIP step are also going to have an impact. And so we wanted to be able to control for those evenly. And so we built a simulator that faithfully performed the expected codec transitions that would happen in a VoIP call. We assumed that the only losses were really from VoIP transmission. We modeled those as faithfully as we could, and we also implemented packet loss concealment or silence insertion in the VoIP step. And we also faithfully modeled GSM air transmission down at the physical layer level and assumed a very conservative rate of GSM air loss according to the GSM specifications. So we did, from there we fed the simulated audio into our Simbox detector. Our audio, by the way, came from the TIMIT corpus, which is high-quality audio recorded for speech recognition research. So we did 462 individual calls just to see how Ammit would fare against individual calls. And then we took another 99 speakers and simulated sets of calls from those speakers to simulate what would happen if you were trying to detect multiple calls from a single SIM. And so I want to show you the results of this work now, starting with the individual calls. So this graph shows our performance with the loss rate as an x-axis variable and the percentage of calls detected as a y-axis. And the first thing that's obvious from this graph is that Ammit clearly depends on the loss rate. But we could have predicted this at the beginning, right? Because we're looking for losses, and so the more losses there are, the more they will be easy to detect. Once you get down into more realistic 2 and 1% loss rates, at 2%, we detect somewhere between 49 and 87% of these calls, just individual calls, mind you. And then once the loss rate drops down to 1%, we see somewhere between 15 to 30% of these calls being detected. Now, this comes at a cost of a 1% false positive rate, and we detail how you can deal with false positives in the paper. So now I want to show you what happens if we look at SIM cards, though. And so in groups of 20 calls, we basically double the individual call performance. So even at loss rates of 2%, we still catch at least 96% of Simbox calls. And in the case of the use of packet loss concealment, it turns out that this is so distinctive and rare compared to human speech that even with 1% of calls, we detect almost 100% of Simbox SIM cards. And even looking at the 1% rates for the other codecs that weren't using packet loss concealment, we still catch between 28 and 43% of those packets. And I want to remind you that, again, these results are conservative because we're not taking into account the source network losses. So we liked our simulated results, but we wanted to make sure that our simulations were faithful. And so we actually went and we bought one of the most popular Simboxes on the market and paired it with a research femtocell and delivered calls from Planet Lab into our Simbox and compared them to calls that we made with a normal phone right next to the Simbox. So we made 100 calls of legitimate and Simbox calls. and 87% of these we were able to detect with no false positives in this data set. And this simply confirms what we expected to see from the simulation results. So I hope I've convinced you at this point that we can detect these calls reliably, but the real question is, can they do so in an adversarial model? It doesn't matter if we can detect these calls if there's a way to easily evade our techniques. And so we make 4 basic security assumptions about the deployment of Ammit, and we think that they're fairly reasonable. For example, we assume that the simboxers rather, aren't going to attack the Ammit software directly. And this is a reasonable assumption because telcos are very good at preserving the integrity of their billing systems, and so we assume that they'll just put this next to the billing equipment and everything will be okay. Second, we assume that Ammit is going to analyze all call audio, not say the first 30 seconds. Because if we do that, then simboxers will just wait 30 seconds to start the simboxed audio. This is not a big problem because our implementation that was slow and written in MATLAB by a grad student could handle up to 10 times more calls than you would normally see at a tower at a given time. So performance is not an issue. The third thing is that we report single call judgments to a central location so that you can't move around and make different calls in different areas and hide from Ammit. And finally, for the similar reasons, we assume that Ammit is widely deployed because Ammit can't analyze call audio that it can't see. So even with these assumptions, there are still a few ways that simboxers could evade our system. And we go into great detail in this in the paper, but I want to give you sort of an outline of the things that they can do and the reasons why we think that won't work. The first thing that they could try is to simply avoid packet loss on the VoIP step by using lots of retransmission or just sending redundant audio streams. So you have one call, you send 2 packets for every packet of audio. So the thinking being that if you have one packet that's lost, the other one will get through and you'll still be able to recover all of the audio and there'll be no losses to detect. This was a suggestion by one of our anonymous reviewers, so thank you, whoever you are. But we don't think that this is going to work because it doesn't reflect the impact of losses that happen at the source network. So we think that those will be also able to be detected, and so just simply improving the IP link quality won't work. The second thing that an adversary could try to do is to try packet loss concealment algorithms that Ammit doesn't know about. And we've got a few reasons to believe that this won't work either. The first of which is that they fall into 3 main categories, and each one of them we believe is algorithmically detectable, and we've done implementations for several of them. And those that we don't know about tend to be similar to ones that we do. And our actual Simbox that we used for testing is a great example of this. It was not actually using the GSM codec, and it wasn't using the strict GSM PLC algorithm, but we were still able to detect it with 87% accuracy as if it were GSM PLC because they were doing something similar, though not exactly the same. The last thing that they can do is fairly technical, but it involves fooling Ammit into believing that losses from the early parts of the Simbox call are actually over-the-air transmission losses. In effect, fooling us into thinking that all losses are legitimate ones. To do this, they would have to first detect all detectable losses. So they would have to run Ammit themselves, but then they would have to buy customized GSM radio hardware to transmit frames with bad CRCs. This is going to be very prohibitively expensive because no currently available stuff on the market will let you do this. Things like Osmocom BB won't scale because it's already hard to get those phones and you're not going to be able to get hundreds of them. And finally, software-defined radios won't work because they're 2 orders of magnitude more expensive than existing Simbox equipment. So with that, I want to leave you with the 2 main takeaways of this paper. The first is that the use of simboxes for interconnect bypass fraud represent a threat to the reliable function of cellular networks that billions of us rely on every day. And the second takeaway is that we can actually stop these calls by using call audio to detect Simbox calls in real time, stopping them at the source before they become profitable. With that, I want to thank you for your attention, and this is my contact information. I am on LinkedIn, and so I'm happy to take your questions now.
Hi, Rudy Museko, Software Engineering Institute. I thought that was a really neat talk. And actually, you hit me on the term substral and quiferency. I'm going to be looking up that sort of stuff. It's really interesting.
Don't read the Wikipedia. You'll spend days trying to figure it out.
Okay. My question is actually, this is a great technical solution to a problem. But one thing I don't understand is the economics of how the Simbox is actually worthwhile to anyone, because there still would be a cost of the SIM cards and the traffic on the other side. Could you just explain that a little bit?
So we, in early versions of the paper, we actually had a full economic analysis. It's not in the current version. So the idea is that in a lot of places, what they're doing is they're actually evading international call tariffs. So some countries will basically tax international calls. And so what you're normally used to paying is something like 19 cents a minute for an international call. But they can basically do this with an initial capital outlay and then basically pay for internet service and then 2 cents a minute for the local cellular call. So they've got 17 cents of profit, basically. That's sort of the economic model that they're working with.
Thank you.
Kyle Saska, CMU.
Great talk.
Thank you. You too. So I have a question. It seems like there's a bit of an arms race going on here, and on the adversary side, they're looking to reduce the call audio gap between local calls and calls made through their system. Now, if you have a VoIP step that includes a really high latency, this is a usability problem, but in theory and practice, you could have a really high latency VoIP step that is nearly lossless. At that point, what would it mean for your system? And additionally, these SIM cards exhibit certain behavioral patterns that you yourself said are not typical to most users. How distinct are they, and could you sort of use that information as well to help aid in detection of these sort of systems?
Okay, so there's two questions. The second one is, could you use behavior, like billing behavior? And the answer is that is really an arms race. There's been some prior work on it. There was work at IEEE Infocom on this last year, looking at call records. That paper was focused primarily on IMEI numbers, so the actual device identifier, that our cheap Simbox is really good at spoofing. It comes out of the box with this feature. And so realistically, you're just going to force your SIM cards to have more realistic call patterns. And that's why we wanted to do this work focusing on audio, because these features are inherent. Now, if I recall, your first question was about what if I just have a really, really good VoIP connection, right? And the answer is, first, that will never deal with the source network problems. But second, we actually discuss the latency issue in the paper. What if you just have a really wide jitter buffer and do lots of retransmits? And we think that there's actually going to be a good way to detect that using call audio as well, because of the usability issues. So Skype actually has longer latency than a traditional phone call. And so if you remember when you started using Skype, you were interrupting the other person a lot. And so this is called double talk in the telephony field, and you could actually detect that, I believe.
All right, great. Thank you.
Thanks.
So Warren Kamari, can't I create GSM CRC errors by simply injecting noise in the RF section? So I don't actually need a custom GSM chipset. I just time stuff correctly and insert noise before the antenna.
Something like that might work. You would have to be pretty smart about it to make sure that you had enough power to actually hit the tower. You'd have to be pretty smart and hope that your noise took the same path as the legitimate audio. Something like that could work, but you're still talking an order of magnitude more complexity than just buying a gateway off the market and using it.
So as far as the international tariffs are concerned, do those end up going to the telcos providers, or does that go to the government that receives the call?
Well, we're talking about the telco policies of about 150 countries, so it really varies. I think some of them are split, but some may just go to the company and some may just go to the government.
do those same tariffs exist for internet traffic that comes into the country?
As a matter of fact, I don't think that they do. And this is actually a great time for me to highlight that this is not at all about stopping legitimate VoIP traffic. When VoIP calls come into a country where these frauds are particularly a problem, the governments aren't concerned about it. They're coming in through licensed gateways that aren't piggybacking on the cellular network and causing cellular network problems.